How do we represent motion on a sheet of paper? Apart from writing on it, that is. A cartoonist might add some speed lines like this, but a scientist uses a graph. For the exam, you need to know about two types of graph: distance time graphs and velocity time graphs. First, let's look at distance time graphs. These graphs can be used to represent a journey. And we're nearly there yet. The vertical axis shows the distance travelled from the start point. The horizontal axis records the time. All we need now are the journey details. So here's me on my bike, and I set out from where I live. Might only have one door and a chimney, but it's home. And I'm on my way to visit my gran. I spend half an hour at my gran's eating cake, chocolate, mint imperials, cough sweets, and all those cake bars that are neither cake nor chocolate, but somewhere in between. My distance from home doesn't change during that time. Then I come home, experiencing quite an intense sugar crash, but not a bike crash, obviously. I'm just riding a lot more slowly. So what can we learn from a distance time graph? The slope of a graph tells us a great deal. If the line is horizontal, then no distance is travelled, so the object must be stationary. If the line of the graph is sloped but straight, then the object is moving at a steady speed. I came back from my gran's less quickly than I went there. With that much cake on board, you're going nowhere fast. The line sloped more gently when I moved more slowly. Now, on to the second type of graph you need to understand: velocity time graphs. Yes, those don't look like speed lines, do they? Let's just stick to the science. On a velocity time graph, the vertical axis is velocity and the horizontal axis is time. Now here I am taking Gran to the seaside. Spain, in fact. She likes the food. Here is my speedometer. Okay, it's not my speedometer. No way, it's my story. Let's say I'm the pilot. Take off. Our speed goes from 0 to takeoff speed pretty quickly. I'm quite a smooth operator when it comes to my job. We keep accelerating as we climb. Then, we're at a nice steady cruising speed. Autopilot on. I pop back and chat to Gran, but she's watching Kung Fu Panda. So I try and chat up the stewardess. Hey ladies, great takeoff again, yeah. Whatever. Now there's no acceleration going on, and notice what's happened to the graph. It's a horizontal line, but we are certainly still moving. That's a big difference between velocity time graphs and distance time graphs. Horizontal lines mean different things on each one. And coming to land, we decelerate and come to a nice gentle halt. Our velocity is 0 again. So what does a velocity time graph tell us? A horizontal line means there is no change in velocity. Be careful, it doesn't necessarily mean the object is at rest. If we have a sloping line, then we have a change in velocity. The object is accelerating or decelerating. The steeper the line, the greater the acceleration or deceleration. And another thing, in distance time graphs, if the line goes back to 0, it means we have returned to the starting point. But in a velocity time graph, returning to 0 just means we've stopped moving. We're certainly not back at home. Before we finish, you need to know a few facts about working out speeds and accelerations. Let's first recap some basics. You can work out speed if you know how far something has travelled in given time. For example, suppose a car travels down a road 300 metres long and it takes 20 seconds. Its speed is how many metres it's travelled each second. So its speed is 300 divided by 20. That's 15 metres per second. If the car covered the same distance in 30 seconds, it would be going more slowly, and in that case the speed would be 300 divided by 30, which is 10 metres per second. So speed is distance divided by time, as in metres per second or miles per hour. Acceleration is the change in velocity in a given time. For the exam, you only need to be able to calculate constant, steady accelerations. Okay, just pretend this is a steady hand. Suppose a car accelerates from a rather gentle 5 metres per second to a scarily fast 35 metres per second, and suppose this speed up takes only 10 seconds. Not only is this a pretty nifty car, the driver must be a mentalist! The change in velocity is from 5 to 35 metres per second, so an increase of 30 metres per second, which took 10 seconds to accomplish. So it increased its speed by 3 metres per second for each of those 10 seconds. Or, to put it another way, the acceleration is 3 metres per second. Or, you can say, 3 metres per second squared. Energy, momentum, forces and work. And some other stuff that's on the floor now. But how do they all fit together? First of all, work. What is work? Good, honest work. But how do we measure it? Well, work and energy are measured in joules. Work comes from force and distance. Remember how? Of course you can. That man pushing a rock image is pretty unforgettable. Well, it works like this. Here's a block. I push it in this direction for 3 meters. I'm using a force of 100 newtons, as you can see. And I've travelled 3 meters. All we need to do is multiply the distance by the force. So 3 meters times 100 newtons equals 300 joules of work. When you move a force over a distance, then you have done work. Now on to energy. Kinetic energy, potential energy, elastic energy, heat energy. Energy can change. A fast-moving bike wheel will transform its kinetic energy into heat energy pretty quickly if you brake suddenly. Next, pork pies. You can use a grapefruit if you're on a diet, but there's no real reason to, as we're not going to eat it. The point is to lift an object off the floor and put it on a shelf. Why not? It takes some work to lift the pie against the force of gravity. This work gets transformed into gravitational potential energy. That's the energy that would be released if it fell. If it fell. Now, the pendulum. When it swings, 2 forms of energy are transformed back and forth between each other. But how do you know which? When you pull the ball on a pendulum out to the side, it moves up too. It is higher up, so it has gained gravitational potential energy. Remember the pie. Same principle, but less messy. Now we let the ball go. What happens to the energy? Well, as it falls, it loses height, so loses gravitational potential energy. But it starts moving faster and faster, so it gains kinetic energy. As it swings back up higher, it gains gravitational potential energy again. But also, as it swings up, it slows down and loses kinetic energy. Over and over, the energy is transformed back and forth. Gravitational potential energy to kinetic energy. GPE, KE, GPE, KE, GPE, KE, GPE, KE, Oh, you get the picture. Each swing will be slightly less than the previous one, as some energy is transferred to the surroundings, mostly as heat, but not much heat. Kinetic energy isn't just for pendulums. Anything moving has kinetic energy. It's all about mass and speed. Kinetic energy equals half mass times velocity squared. Velocity, of course, is speed. Suppose a 1,000 kilogram car is travelling at 10 meters per second. That's 36 kilometers per hour, by the way. Go granny. The car's kinetic energy is given by half the mass times the speed in meters per second squared. So that's half times 1,000 times 10 times 10. So that's 50,000 joules or 50 kilojoules. It all makes so much sense. Now, momentum. What is it? Momentum is also about mass and velocity, but its formula is simpler. The momentum of an object is its mass times its velocity. The more mass you have, the more velocity you have, the more momentum you have. Now, if you lose that momentum quickly, you will feel a large force. Lose momentum more gradually, and you'll feel less force. There's another thing about momentum you need to know. When something explodes, its total momentum before is the same as its total momentum afterwards. And also in collisions and crashes. Let's look in more detail at the cannon. Total momentum before the gun fires is 0. Nothing is moving. After it fires, the cannonball is moving forwards. That's momentum in a forwards direction. The cannonball has small mass and large velocity. Momentum in the backwards direction will cancel this out. The cannon recoils backwards. It has large mass but small velocity. The two objects, cannon and cannonball, have equal momentum in opposite directions. They cancel out. That keeps the total momentum equal to 0, which is why we get recoil when guns fire, and how jet engines work, how rockets fly, and how balloons do their thing. Not that you're ever going to get to see all that at once, unless you go to a NASA-sponsored military-themed jet pilot birthday party. But you never know.